All right, excellent. All right, so let's see. Newton's law, right? So I'm just going to go over the gravity right now and just do gravity so we can all understand what gravity is. Plus, when we talk about black holes, you have to understand gravity. And there's something that also creates the tides on Earth as well. So this gravity I'm going to be talking about right now is kind of important, right? So let's see what this gravitational formula is all about one more time. We said the force of gravity, right? I'll write it down again. Force of gravity is equal to that thing we call the gravitational force. This is the constant. It's called the gravitational constant. So this is a constant. Constant of gravity. This constant of gravity has to do with mass. Well, what is mass in our universe like? Like, so if you have the Earth and you want to get the mass of the Earth, you need this gravitational constant. You have to get this gravitational constant. And the way you do it, you have to have like two balls, one of them really a massive ball and one of them really a light ball, like a small ball next to the big giant ball, hanging on a wire. Like in my room, I have a big giant ball and a little tiny ball, right? Like this. And then how much this massive ball makes this little ball move towards it. It's an extremely difficult thing to do because the Earth's gravity is pulling both of them down. So what they do, they get two balls and two little balls and two big balls, and they hang them all, and then the balls will twist a little bit. And by looking at the wire, the twisting of the wire as the balls get attracted to the big balls, to figure out the gravitational constant. And you have to do it outside. Like you get a little telescope, you go out, you watch this wire. This like it was done in the 1800s, and it's just extremely difficult to do. We're still doing it. We don't know the gravitational constant probably as good as we should know it, right? And something else that I read last week, which was really incredible. Somebody figured out a mass of an atom, one single atom. They dropped it in vacuum and it fell to the ground at the same speed as everything else in the universe, which is incredible. How do you do that? How do you get an individual atom, you drop it, you know? Like if you see my little finger here, my little finger here has something like 10 trillion atoms in it. This little finger here, 10 trillion atoms. That's incredible, right? All right, so that's what this is. It has to do with the mass of the atom in this universe. In other words, what is a proton's mass in this universe, basically? Then we have mass of the first object times the mass of the second object. Divide that by the distance between the masses to the power of 2. So this is distance between mass 1 and mass 2 to the power of 2. That to the power of 2 is all important. Because if the gravitational force was only dependent on your distance, then it'd be a different universe altogether, right? So it is really the distance to the power of 2. So if you move away from the Earth, gravity becomes a lot less. If you move more, gravity becomes a lot more than before. So gravity keeps changing with the distance to the power of 2. So if you move away from the Earth twice, gravity will be 4 times weaker. If you go away from the Earth 10 times, it'll be 100 times weaker, not just 10 times weaker. And that's an important thing to know. All right, so we rewrite this so it'd be easier to see. We say force of gravity is equal to the G that you don't ever have to worry about times mass 1. And when we say mass 1 times mass 2, that multiplication sign is never used. You just say mass 1, mass 2. It implies, right? Implies multiplication, right? Divided by this distance to the power of 2, like that. Okay? All right, so now I'm going to have somebody leave the Earth And as they leave the earth, see how much their weight will fall. Now, what is weight again? Weight is the force of gravity. So this is weight, basically, right? Say this is weight. So that's your weight. And it has to be on the ground. Like if you're flying around, then your weight is not the same. If I jump on the off the table, then while I'm in the air, before I hit the ground, I'm weightless. Only when I hit the ground would I have weight. Now, everything that falls towards the earth is going to be accelerating 32 feet every second. So if you drop something, it'll move towards the earth. It will accelerate 32 feet every second. So the second is going to be 64 feet per second, right? In other words, it'll be 64 feet if I drop something. In 2 seconds, it goes 64 feet. In 3 seconds, it goes 96 feet, like that. So it keeps accelerating at the same rate. It's a constant rate of acceleration. Anything that happens on in the air here falls towards the ground at that rate, 32 feet per second. Every second, it accelerates that much, right? 32 feet per second. So let's see. So this is the big formula here. So I'm going to use that formula now to see how much we weigh. You know, what's our weight? Now I'm going to erase that, but before I erase it, I'm going to put this formula someplace here so you can keep an eye on it all the time. Force of gravity is equal to G times M1 times M2 divided by D squared, right? So I'm going to erase this now and see all that it means. Here's the Earth. And the center of the Earth is the center of gravity of the Earth. So everything that we measure is from the center of the Earth, because the Earth's gravity, it acts as though it's at the center of the Earth. So all the forces are pulling everything towards the Earth. Now, later on, I'm going to say, and don't get confused, because this is an explanation from the 17th century. Einstein is going to come in the 20th century and say this is all wrong. It works just great, but it doesn't really work when there's a lot of mass, like in a black hole. If there is speeds that are close to the speed of light, things like that, it does not work. So it's not a correct formula, but it's an approximation. And this approximation is so good that we went to the moon using this approximation. So no worries for us in this class. All right, now I'm going to have a person on the surface of the Earth here. And let's put this person right maybe here. There is a person, and we say the mass of this guy is M1. Mass of the Earth is M2. So M2 is equal to the mass of the Earth. M1 is equal to the mass of person. And we said the distance between the two, the distance between the center of the Earth and this guy here, we're going to call that D. That's the D, the distance between the center of the Earth and this person. So D is the distance. D is the distance. And let's say this guy here has a weight of, let's make it 200 pounds, all right? So let's say this guy here, weight on the Earth's surface for our subject is 200 pounds. All right, 200 pounds. Okay. So this guy gets on a scale and he weighs himself and it's 200 pounds. Now we want to see how much does his weight fall. You want to know when does he become 100 pounds? When does he become 200 pounds, 300 pounds, whatever. See what happens. So this guy here is going to move away from the Earth twice as far away from the Earth. So instead of D is going to be 2D. This is 1D. This is another D. So now we have 2D. This distance here is 2D, right? From the center of the Earth to this guy now is 2D. So how much does he weigh now that is moved away twice as far away from the Earth? 1D plus another D. All right, so we'll write the formula one more time. We say force of gravity is equal to G times M1 times M2 divided by 2D squared, like that. So 2D squared, that means 2D times 2D. D times D is D squared, 2 times 2 is 4. So this would be 4D, right? So this would be 4D squared, like that. 4D squared. All right. So now that it's 4D squares, I can rewrite it. I can take the 4 out. Because remember I said we can multiply everything times the same number on one side and the other side. So we can move it out here. Instead of it multiplying here, we can just move it here. So the force of gravity is equal to 1/4 now of G times M1 times M2 divided by T squared. All right, so his weight dropped 4 times. Now, what is the radius of the Earth? It's about 4,000 miles from the center of the Earth to here. So if you move 4,000 miles away from the surface of the Earth, you'll be in space someplace 4,000 miles away from the surface. This is 1/4. So that means that this guy is 200 pounds. To be 1/4 of 200 pounds, 1/4. So this would be force of gravity for this guy was 200 pounds. Now the force of gravity is 1/4 of 200 pounds or 50 pounds. So if you go 8,000 miles away from the center of the Earth or 4,000 miles above the surface of the Earth, you weigh 50 pounds, like that. All right, so let's go 4 times away from the center of the Earth and see how much your weight will fall, right? Or how about 10 times farther, right? So we go 10 times farther from the center of the Earth. We go 1D, 2D, 3D, 4D. So we're going to be 10 times D farther. Now what happens if you go 10 times farther? How much would it drop now? Okay, well, let's do the same exact thing again. So we're going to do force of gravity is going to be equal to G times M1 times M2 divided by 10D to the power of 2. 10D is going to be equal to 100D squared. So this would be 100th. Well, actually, let me write it out so I don't want you guys getting confused here. G times M1 times M2 divided by 100D squared. So now his weight has gone down 100 times. All right, so what's 200 divided by 200? Force of gravity now is going to be equal to 200 divided by 100. So that means he weighs 2 pounds. If he goes 40,000 miles away from the center of the Earth, which is 10 times the distance between the Earth and this guy now. So here we go twice as far. Our weight is 4 times less. 200 pounds will be 50 pounds. If you go 100 times farther, then your weight is going to fall 100 times less. 100 times less weight. So that's why it's 2 pounds.
So now I think I'm a little confused about something about how you're plugging in the numbers into the formula, but
Okay.
like I don't know which one you want to do, maybe the one you're looking at now, but so when you plugged in 10d squared, I understand how that turned into 100d squared, no problem there. I'm a little confused about where and when you plugged in the mass of the earth and the mass of the person.
Well, you don't have to plug in anything. You don't have to plug in the guy's mass or the Earth's mass. We're saying that the Earth's mass doesn't change, right?
Sure.
We're saying the guy's mass doesn't change either.
Sure.
So we don't have to worry about this guy's mass or the Earth's mass. That's not something we have to worry about.
Okay.
Because we're just trying to find out how much it's dropping.
Gotcha.
Yeah. Otherwise, I'm gonna have to put the mass of the Earth and the other mass and everything. That'd be ridiculous. So
okay, so then my question is, how you got from the force of gravity equals G times M1 times M2 over 100d squared, how you got from that to the one right below it, F force of gravity equals 200 over 100 equals 2 pounds.
Oh, this one here?
Yeah.
Okay, same way here. Force of gravity is equal to 100th times M1, M2 divided by D squared.
Okay.
Right, like that. You can take the 100 that is multiplied times D2, you can take it out and put it anywhere you want, right?
Got
this
that.
way, I'm showing you exactly 100th. Here, you should be able to figure it out, but maybe your math is not good. Not to worry. We're just trying to figure it out. So
okay, so I understand that you move the 1/100ths out and then multiply it. So then from that point, how do you get to force of gravity equals 200 over 100?
I forgot to put the G here, though. Okay. This is G, right? Let's not forget G. All right, so here it is. We said that formula is force of gravity is equal to, right? G times M1 times M2 divided by D squared, right?
Yeah.
Okay. And this was 200 pounds. This is force of gravity is weight. Right? So this is 200 pounds. Force of gravity is equal to G times M1 times M2. On the surface of the Earth, that's what you get. 200 pounds. We already weighted this guy. We know this guy weighed 200 pounds, right?
Uh-huh.
And so now the difference between this formula and this formula is just the 100th. That's the only difference.
Which you found out just by doing the distance.
200, yeah. So this is equal to this. 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 Force of gravity is F of G is force of gravity.
So the only thing that we're really plugging in is the distance.
Correct. Because we already know this guy weighs 200 pounds, we just want to know what happens to him if he moves away from the Earth.
Gotcha.
Yeah. So now, here's a question now. Why is it that the astronauts on the space station are floating around, like, so it's free floating around? How far away are they that they're weightless, right? They got to be really, really far to be weightless. Well, the answer is just a couple hundred miles. So why are they weightless at a couple hundred miles? That's what we're trying to get to. In other words, according to our formulas, they shouldn't be weightless, right? They should still have weight. Why are they weightless? That's the question. So why are they weightless? Let's take a look.
Wait.
I'll try it again.
I just need the formulas still.
Oh, this is going to be there. I'm not going to touch that. Is that what you're worried about? I'm not going to touch that. Don't worry. All right, so let's draw the Earth one more time here. See what's going on here. So here's the Earth. And then the space station now is in orbit What does that mean it's in orbit? What does that even mean, right? So let's see. I'm going to have a guy here on the surface of the Earth. And this guy, he loves AK-47 guns, all right? So he's going to be shooting AK-47 guns now. So let's put this guy here. There's a guy with an AK-47 gun, all right? He's going to be shooting his gun. Now, what happens normally if you shoot a gun? Well, your bullet comes out, and then it kind of peters out, right? It goes like that, right? Why does your gun not go forever? You should shoot the bullet. It'll go forever. If you did that in space, your bullet will go to infinity. You go to God himself, right? So why is it falling? Two things. One is the friction between the air and the bullet. So the bullet slows down because of the air. If you guys done any hunting or shooting or anything like in a range, you know that when it's windy and the wind is coming, let's say from this direction, right? You want to kind of shoot in this direction so that the bullet eventually will go right just a little bit. Or if you're a quarterback, right? If you're a quarterback on a windy day, you're trying to throw over there and the wind is blowing this way, you want to throw it a little farther out so that the wind will move it. That's air friction, right? So on Earth, you've seen air friction. Like if you have a feather, you drop the feather, it doesn't fall at the same rate as a heavy ball. It should though. On the moon, a feather and a bowling ball, they drop at the same exact rate. The only reason that the feather doesn't fall as fast as a bowling ball is that there's air friction. So the feather does this, right? All right, so that's one thing. It slows down because of air friction. And then there is gravity on the surface of the Earth. So the gravity is also bringing it down, right? Like that. So you can't shoot forever. But if you shoot it at just the right speed, you can shoot it. It might even go around the Earth. Eventually you'll fall because there's air friction, right? However, if there was no air friction, it'll go around the Earth. Just at the right speed, it will just go around in the Earth, and your bullet will be in orbit around the Earth. That's not going to happen. Why not? Because there's air friction here. That slows down the bullet. But what if you go outside of the atmosphere where there is no air? Well, then you can shoot it, and this will go around the Earth, and it'll be in orbit. So in orbit means that your motion is so fast that you're basically defying the gravitational force. So the gravitational force is not going to bring you down. So now let's put something in orbit. I'm going to put this guy in orbit now. So let's see. I'm going to put somebody in orbit here. Now there's no air friction. We're outside of the Earth's orbit. So we have an International Space Station a couple hundred miles up. So let's put this guy a couple hundred miles up in a spaceship. Let's say this is International Space Station going around the Earth. And it looks maybe something like this. All right, something like that, all right? Now, what is it doing exactly? Well, what it's doing is the following. So this motion is actually two components to this motion. So we'll break down his motion into two components. One of them is that he's going this way. And at the same time, he's falling towards the Earth. So these two motions is what is really doing according to Newton. So you continuously move and fall towards the Earth. Move and falls towards the Earth. Move and falls towards the Earth. Move and fall towards the Earth. That's what the orbit, according to Newton, is like. Now, if you're moving and falling towards the Earth, this falling towards the Earth is called free fall. Even though it looks like a beautiful circle, it's not really a beautiful circle according to Newton. In fact, that's what calculus is about. Calculus is about like predicting where the motion is going to take it, but yet break it down to little tiny chunks like this, you go, okay, so this motion is really like this. You go, you draw a line from the center of the earth to the motion of this guy here. So you go, what it's really doing here is that it's moving this way, and then it's falling towards the earth. Now, this motion here is a line perpendicular to this green line. So if you draw a green line here, this motion that I just drew is a perpendicular line to here, like that. But at the same time, it's falling to the center of the earth, too. So at the same time, it's falling to the center of the earth, like that. And this means that the guy is moving, all right, around the earth in orbit, but its orbit is really moving this way, falling towards the earth, moving this way, falling towards the earth. If you're falling towards the earth, you're weightless. Now, is that true? Are you weightless if you fall towards the earth? Well, you can go to Disneyland and experience this for yourself. It's called the Tower of Terror, and it's going to open up in April. So you sit there on this Tower of Terror, and they drop you. They just drop you. So the gravity of the earth is going to pull you towards the earth. You're going to be accelerating at 32 feet per second. So the first second, 32 feet. Second, another 32 feet per second. So in 2 seconds, you're going at 64 feet. All right, 64 feet, you've dropped. Third second, you'd be 96 feet, like that. You're just dropping, free falling. At that point, you're weightless. So if you put, let me see if I can raise my leg here. If you put a dime here, can you guys see my leg? If you put a dime here, then the dime will float above your knee. I don't know, a lot of people do it. If you go there, check it out. But there's another way of doing this too. The other way of doing this is the following. You get an airplane, and the airplane goes way up in the sky. Let's say 40,000 feet. After it gets to 40,000 feet, then the airplane will drop like this. And as it's dropping towards the earth, it's free falling. Free falling means that you have no weight, so you're weightless. And they do that all the time. In fact, the entire movie with Tom Hanks on the Apollo 13, it was made inside of an airplane. They took the airplane up, then they drop like this. As they drop, they start shooting, because everybody in the airplane, I mean, shooting not with a gun, but with a video camera, right? So they all appear to be really weightless. The entire movie was made inside of that airplane. That was a NASA airplane. There's some drawbacks. Like, for one thing, puking. Puking happens there all the time. So if you puke first few times, you have to get used to it. Then after that, everybody's okay. I guess they made the entire movie like, hours and hours and hours inside the airplane. Now, I was going to show you guys this. So remember, I haven't seen the entire video to make sure there is no F words in it. So there may be 1 or 2 F words. This girl has got a dirty mouth. But so do I. I mean, I use the F word all the time, but never, ever in the classroom. So I tried to start it where there's no F words. And then I'd like to show you guys Stephen Hawking, the smartest man that ever lived after Sir Isaac Newton. Stephen Hawking, I was going to show him in the airplane. For the first time in his life, he's going to be floating around weightlessly because it's dropping, free falling towards the earth. You can also jump out of the airplane without a parachute, and you'd be, basically the same scenario. You'd be weightless, and you can do somersaults, you can do all kinds of stuff on the way down. You're still going to be falling towards the earth, but as you fall towards the earth, you're weightless. So has anybody ever done that? Has anybody ever jumped out of an airplane?
I have.
You have? What was it like? Tell us. Please.
It felt like you were floating.
Felt like you were floating. Okay. That makes sense. All right. So let's watch this 4-minute movie together. Let me see if you guys will enjoy this. It's kind of an interesting thing. And for sure, it's going to be on the exam. So there's going to be 2 questions when we talked about today. One is, why are you weightless if you're in orbit, even though the space station is only 200 miles up? Well, because you're free falling. It's a continuous free fall. So that's the reason that you're weightless inside the space station. That's one reason. Second thing I was going to ask you is, let's say you weigh 100 pounds and you move away from the surface of the Earth, say twice, right? Well, then you say 2 times 2, 4 times less weight. So if you're 100 pounds, you'd be 25 pounds. Let's try one more. Let's say you are 100 pounds and you move away from the Earth 10 times the distance between the center of the Earth and the surface of the Earth. How much would you weigh now if you go 10 times farther, 10 times 10, 100 times less weight? If you're 100 pounds, you'd be 1 pound if you go 10 times farther from the surface of the Earth. That's just those 2 questions will be on the exam, all right? Okay, so let me share these videos with you guys. It's kind of fun, actually. I like this stuff. All right. It says, so we went to San Jose because I got a ticket to the Vomit Comet, and she had to get up at 6 o'clock in the morning to do it. And so this is the story of this girl, and there's only 2 minutes of it left. So let's check this.
I was really freaking nervous about it because a lot of people do throw up. And if you throw up, you have to get back in your seat for the rest of the flight. So basically, it'd be the most expensive vomit of your life. Unless you like threw up into somebody's Gucci bag. For each parabola, you get about 30 seconds of weightlessness. And we did 15 of them. So I got about 7.5 minutes of glorious weightlessness. So without further ado, here's some footage of me having the freaking time of my life. So I was supposed to narrate this as it went, but I could get no intelligent commentary out of myself. I have no idea what's Yeah, that's about it. As the airplane's going up, you're laying down on your back, and first you're getting heavier and heavier and heavier, but then you're getting lighter and lighter and lighter until you just float out. It was really like flying, and your body doesn't really know what to do. Like, your instinct is to just pedal, which is terribly ineffective. Oh my God. You threw out some water and got to catch some candy. I feel like fucking Pac-Man. So yeah, here we are. Also, I cut my hair because I felt that I wanted to look even more like one of the Hanson brothers.
Okay, so now let me show you Stephen Hawking is in space.
Why should we go into space? It will completely change the future of the human race, but maybe determine whether we have any future at all.
Stephen Hawking warned us that our days on Earth are numbered.
I fear for our future. Our planet, Earth, is threatened with an ever-expanding population and only finite resources.
Over the years, he gave bleak estimates on our expiration date on this planet, ranging from 1,000 years to a chilling 100. But in his mind, the solution was simple.
If our species is to survive, it is imperative we voyage out into the blackness of space with a determination to colonize new worlds across the cosmos.
Despite his illness, Hawking got as close as anyone on Earth can to exploring the cosmos.
In 2007, I was lucky enough to experience microgravity on a zero-G flight. For me, this was true freedom. People who know me well say that my smile was the biggest they'd ever seen. I was Superman for those few minutes. I have always dreamed of space flight, but for so many years, I thought it was just that, a dream.
In 2016, his dream came one step closer to coming true.
Richard Branson made it his mission to make space flight a reality for those intrepid enough to venture beyond the boundaries of the Earth's atmosphere.
Branson unveiled the VSS Unity, Virgin Galactic's newest spacecraft that promises to one day carry tourists into suborbital space. Hawking got the honor of naming the craft, but that's not all.
Richard called me from Necker Island to offer me a seat. I said yes immediately. I never thought I would have the opportunity to see our beautiful planet from space or gaze outward into the infinity beyond.
Ultimately, Hawking wasn't able to realize his spaceflight dreams, but his conviction will continue to shape future generations of space explorers.